Hello everyone. Today we will study hypergeometric distribution. First of all, let me introduce what it is. Consider a set S. Which contains n1 success and n2 failures. Consider S. It contains n1 success and n2 failures. Consider next set S. In set S, it contains n1 success there are n1 success and there are n2 failures. This is set S. There are n2 failures. I use F to represent failures. Consider a set S. In set S, there are n1 success and n2 failures. Assume the chance of getting each element is the same. Assume the chance of choosing each element is the same. When n elements are randomly chosen from the set, without replacement. When n elements are randomly chosen from the set without replacement, assume this n is less than n1 plus n2. We cannot choose more than n1 plus n2 elements. n1 plus n2 represent the total number of elements in the set. We cannot choose more than n1 plus n2 elements. For example, if there's only 10 elements in the set, I cannot choose 12 elements. I can choose at most 10 elements. So n must be less or equal to n1 plus n2. When n elements are randomly chosen from the set, then the random variable x represent the number of chosen success. Let the random variable x represent the number of chosen success. Then we say this random variable x has a hypergeometric distribution. Then we say this random variable x has a hypergeometric distribution. And its probability function is what? How do we write probability function? Probability is always number of favorable outcome divided by number of all possible outcome. What's the number of all possible outcome? There are totally n1 plus n2 elements in the set. In the set, there are n1 success, n2 failures. So there are totally n1 plus n2 elements, and we are choosing n elements out of the total. For the denominator, there are totally n1 plus n2 elements, and we are choosing n elements out of the total. That's the denominator. On the numerator, number of favorable outcome, we are choosing n elements out of the set. We are choosing a total of n elements out of the set. If there are x success, then how many failures do we choose? If we choose a total of n elements, if there are x success, then how many failures do we choose? Total is n. If we choose x success, what's left is x, m minus x. So we choose m minus x failures. If we choose n x success, what's left is m minus x. Those are failures. So for favorable outcome, there are totally n1 success. We choose x out of n1. There are totally n1 success. We choose x out of n1. And there are n2 failures. There are totally n2 failures. We choose m minus x out of n2. So that's the number of favorable outcome. That's the number of all possible outcome. That's the probability. Next, what's the support of x? What's the support of x? Support of x represents a set of all possible x value. Support of x represents a set of all possible x. If I choose n element from the set, what are the possible value that s could be? What are the possible value that s could be? We know that x by itself must be greater than 0. Since we choose x success, x by itself must be greater than 0. X cannot be more than n. S cannot be more than n. We cannot choose more than. Number of success cannot be more than the total number of total elements. Number of success cannot be more than the total number of total elements. And also, x must be less or equal to n1. X must be less or equal to n1. Since there are totally n1 success, I cannot choose more than n1 success from the set. X must be less than n1. Also, we know that there are n2 failures. There are totally n2 failures. We choose m minus x failures from the set. So n minus x must be less or equal to n2. We cannot choose more than n2 failures from the set. We cannot choose more than n2 failures from the set. So the number of chosen failures must be less than the total number of failures. So m minus x must be less than or equal to n2. Next, based on these three inequalities, we try to find a restriction for x. These two equations are clear, they have x by itself. But this inequality is not clear. We try to get x by itself. In this inequality, we try to get x by itself. So if I add x on both sides, I have n less or equal to n2 plus x. If I subtract n2 from both sides, then m minus n2 is less or equal to x. So let me put this inequality together here. X is greater or equal to n minus n2. Now next, let's try to find a restriction for x here. X must be greater than 0, and it must be greater than m minus n2. X must be greater than 0, and it must be greater than m minus n2. Since x is greater than both numbers, it must be greater than the larger number. Since x is greater than both numbers, it must be greater than the larger number. If x is greater than larger number, then it's greater than both numbers. So x must be greater than the maximum of 0 and m minus n2. X must be greater than a larger number. So x must be greater than the maximum of 0 and m minus n2. If x is greater than a larger number, then x is greater than both numbers. On the other side, x must be less than both n and n1. X must be less than both n and n1. So if x is less than both numbers, then x must be less than the smaller number. If x is less than the smaller number, x will be less than both numbers. So x must be less than the minimum of n and n1. X must be less than n and n1. X must be greater than the maximum of 0 and m minus n2. And s must be less than the minimum of n and n1. S must be between these two numbers. That's the support of x. So support of x must be an integer. X must be a whole number, must be an integer. And x is between the maximum of 0 and m minus n2. And it must be less than the minimum of n and n1. This is hypergeometric distribution. The notation is if x has a hypergeometric distribution, notation is x is hypergeometric distribution for hypergeometric distribution, there are three parameters. For hypergeometric distribution, there are three parameters: n, n1, and n2. For hypergeometric distribution, there are three parameters: n, n1, and n2. n1 represents the number of total success. Here, n1 represents the number of total success. N2 represents the number of total failures. N represents the total number of chosen element. N represents the total number of chosen element. X represents the total number of chosen success. This is lowercase x. This is lowercase x. This is capital X. Capital X represents random variables. This is capital X. This is lowercase x. This is lowercase x. This is also lowercase x. X represents the total number of chosen success. X represents the total number of chosen success. This is hypergeometric distribution. Next, let me show you an example. Let X be a hypergeometric distribution with perimeters 10, 20, and 30. Find each of the following probabilities. Find each of the following probabilities. Part A. What's the probability that S equal to A? This is capital X. This X represents random variable. Part B. What's the probability that S equal to 5? Part C. What's the probability that S less or equal to 2? Part D. What's the probability that X is greater than A? In this format here, S is hypergeometry 10, 20, 30. There are three perimeters. First number always represents the lowercase n. Second number always represents n1. Third number represents n2. Don't forget order. Order matters. First number represents n, lowercase n, the total number of chosen element. Second number represents n1, the total number of success. Third number represents n2, the total number of failures. Now let's answer the question. Before we answer the question, let's find probability function first. Always find probability function first. Always find the probability function first, then find the support. Probability function formula is n1 choose n, n2 choose n minus x, so n1 choose x, n2 choose n minus x over n1 plus n2 choose n. So let's plot in numbers. n1 is 20, n2 is 30, n is 10, n is 10. So we have 10 minus x here. In the denominator, n1 plus n2. 20 plus 30 is 50. N is 10. This is the probability function. This is the probability function. Next, find support of x. Next, find support of x. What's the maximum of 0 and n minus n2? What's the maximum of 0 and n minus n2? Let's compute the maximum of 0 and n minus n2 first. n minus n2, 10 minus 30. n minus n2, 10 minus 30 is negative 20. Maximum of 0 and negative 20 is 0. Maximum of 0 and negative 20 is 0. Next, find the minimum of n and n1. Next, find the minimum of n and n1. What's n here? N is 10. N1 is 20. Minimum of 10 and 20 is 10. So support of x is the integers from 0 to 10. Support of x is the integers from 0 to 10. 0, 1, 2, up to 10. That's the support of x. So always find the probability function first. Before we answer the question, always find the probability function first, and then find support of x. Before we answer the question, before we try to find any probabilities, always find the probability function first, and then find support of x. Then, based on the probability function and the support, answer this question here. Answer the question here. Part A. What's the probability that s equal to a? Probability s equal to a is f of a. We plug in number a for x. In the probability function, we plug in number a for x, which is 20 choose a, 30 choose 10 minus a is 2, over 50 choose 10. Then use calculator for the rest. Use calculator for the rest. Part B. What's the probability that s equal to 5? What's the probability that s equal to 5? For the probability that s equal to 5, we plug in number 5. That's f of 5. Plug in number 5 into the probability function for x. Plug in number 5 for x. In the probability function, plug in number 5 for x. We have 20 choose 5. 30 choose 10 minus 5 is 5. Over 50 choose 10. Then use calculator for the rest. Part C. What's the probability that x is less or equal to 2? Part C. What's the probability that x is less than or equal to 2? Here, support of x is from 0 to 10. If x is less or equal to 2, then x could be 0, 1, and 2. So we have f of 0 plus f of 1 plus f of 2. Then, for f of 0, plug in 0 for x, we have 20 choose 0. 30 choose 10 minus 0 is 10. Over 50 choose 10. Then for f of 1, we plug in 1 for x. We have 20 choose 1. 30 choose 10 minus 1 is 9. Over 50 choose 10. Next, f of 2. We plug in 2 for x, which is 20 choose 2. 30 choose a. 50 choose 10. Then use your calculator for the rest. Part D. What's the probability that x is greater than a? Part D. What's the probability that x is greater than a? Look at support here. S is between 0 and 10. S is between 0 and 10. If S is greater than A, it must be 9 and 10. If S is greater than A, they must be 9 and 10. That's f of 9 plus f of 10. For f of 9, we plug in number 9 for x. For f of 9, we plug in number 9 for x. We have 20 choose 9 times 30 choose 10 minus 9 is 1 over 50 choose 10. For f of 10, we plug in 10 for x. That's 20 choose 10 times 30 choose 10 minus 10 is 0 over 50 choose 10. Then use calculator for the rest. Use calculator for the rest. Next example, in a class there are 14 boys and 6 girls. When a group of 10 students is randomly chosen from the class, find each of the following probabilities. Part A, what is the probability that there are exactly 2 girls in the group? Part B, what's the probability that there are more than 4 girls in the group? So let's set out a problem first. First of all, we need to recognize what kind of probability distribution it is. Here, in a class, there are 14 boys, 6 girls, and we are focused on number of girls. In this two problem, we are looking for probability of getting certain number of girls. So we can treat girls as success. We can treat boys as failures. In a group, we can treat there are six girls. That means there are 6 success. 14 boys means 14 failures. If in a set there are 6 success, 14 failures, and we are choosing 10 elements from the set, we are choosing 10 students. Consider we are choosing 10 elements from the set without replacement. We cannot choose the same person twice. When we choose 10 students from a group, we cannot choose the same person twice. So that means we are choosing 10 elements from the set without replacement. This random variable is hypergeometric distribution. If I let x represent number of girls, this random variable has hypergeometric distribution. So first of all, let's set down a problem first. Let the random variable x represent the number of chosen girls. Then this random variable x has hypergeometric distribution. Then x has hypergeometric distribution. We need to first of all recognize what kind of probability distribution it is. So here x is hypergeometric distribution. That's a notation. For hypergeometric distribution, there are 3 parameters: n, lowercase n, n1, and n2. Lowercase n represents number of chosen elements. We are choosing a total of 10 students, so lowercase n is 10. n1 represents number of success. Since x represents number of chosen girls, so girls represent success. n1 is 6. n2 represents failures. Since girl represents success, boys represent failures. So there are 14 failures. There are 6 success, 14 failures. X is hypergeometric distribution. N is 10, N1 is 6, N2 is 14. Next, write down the probability function. The formula for hypergeometry is N1 choose X. The formula for hypergeometric distribution is f of x equal to n1 choose x, n2 choose n minus x, over n1 plus n2 choose n, lowercase n. Then plug in numbers. n1 is 6, n2 is 14, m minus x, 10 minus x, n is 10. Denominator is n1 plus n2 over n. n1 plus n2, 6 plus 14 is 20. n is 10. This is the probability function. Next, find the support. Next, find the support of x. Let's first of all compute the maximum of maximum of 0 and m minus n2. N is 10. N2 here is 14. 10 minus 14 is negative 4. Here m minus n2. 10 minus 14 is negative 4. Then we choose the maximum number. For 0 and negative 4, maximum is 0. Next, find the minimum of n and n1. Next, find the minimum of n and n1. N is 10. N1 is 6. So minimum between 10 and 6 is 6. So the support of x, this is capital X, this is lowercase x, this is capital X. Support of x is integers from 0 to 6. 0, 1, 2, 3, 4, 5, 6. This is support of x. Then, based on this information, answer the question. Part A. What is part A asking for? What is part A asking for? What's the probability that there are exactly 2 girls? So part A, we're looking for probability that x equal to 2. What's the probability that there are exactly 2 girls? X represents the number of girls. So part A, what we are looking for is probability that s equal to 2. S equal to 2, that's f of 2. So we plug in 2. We plug in 2 into the probability function here. If we plug in, we have 6, choose 2. 14, choose 10 minus 2 is 8. Over 20, choose 10. Then use calculator for the rest. Part B. What's the probability that there are more than 4 girls in the group? What's the probability that there are more than 4 girls in the group? Here, x represents the number of girls. What's the probability that there are more than 4 girls? It's the probability that x is greater than or equal to 4. Sorry, more than 4 girls, not including 4. So, what's the probability that x is greater than 4? Here we know that support of x is from 0 to 6. Support of x is from 0 to 6. If s is greater than 4, s could be either 5 or 6. If s is greater than 4, s could be either 5 or 6. So that's f of 5 plus f of 6. What's f of 5? For f of 5, we plug in 5 for x. For f of 5, plug in 5 for x. We have 6 choose 5. 14 over 10 minus 5. 10 minus 5 is 5. Denominator is 20, choose 10. F of 6. F of 6. Plug in 6 for x. That's 6 choose 6 times 14 choose 10 minus 6 is 4. Over 20 choose 10. Then use calculator for the rest. Next example. A bag contains 5 blue marbles, 6 green marbles, and 9 red marbles. When 40 marbles are randomly chosen from the bag, find each of the following probabilities. Part A. What's the probability that fewer than 6 red marbles are chosen? Part B. What's the probability that more than 7 red marbles are chosen? So first step, let's try to recognize what kind of probability distribution it is. A bag contains 5 blue marbles, 6 green marbles, 9 red marbles, when 14 marbles are randomly chosen from the bag. So we're looking for the following probabilities. What's the probability that fewer than 6 red marbles are chosen? What's the probability that more than 7 red marbles are chosen? So for each probability, we focus on number of red marbles. For each probability here, we are focused on number of red marbles. We can consider red marble in the set. Red marble in the bag I can consider to be success. And other than red marble, the 5 blue marble and 6 green marble, I can consider these to be failures. So consider 9 red marble are success in the set. 5 blue marble and 6 green marble are failures in the set. So, and we are choosing 14 marbles without replacement. It looks like hypergeometric distribution. So this problem looks like hypergeometric distribution. Let's set out the problem first. Let X represent, this must be capital X. Let X represent the number of chosen red marbles. Let X represent the number of chosen red marbles. Let X represent number of chosen red marbles. Then here X has a hypergeometric distribution. Because we consider the 9 red marble as success, 5 blue marble and 6 green marble as failures. So for hypergeometric distribution, N is 14. Since we are choosing 14 marbles from the total, N is 14. N1 is number of success. We consider 9 red marble as success, so there are 9 success. N2 is number of failures. N2 is number of failures. We consider 5 blue marble and 6 green marble are failures. So together there are 11 failures. We have 9 success, 11 failures. This is hypergeometric distribution. This random variable X has hypergeometric distribution. Next, let's find the probability function. Next, let's find the probability function f of x. Formula for hypergeometric distribution is n1 choose x, n2 choose n minus x, over n1 plus n2 choose n. That's the formula for hypergeometric distribution. Next, plugging numbers. N1 is 9, N2 is 11, m minus x is 14 minus x. Denominator, N1 plus N2, 9 plus 11 is 20, n is 14. Then, next, try to find a support. Next, try to find the support of x. For support of x, let's first of all compute the maximum of 0 and m minus n2. Let's first of all compute maximum of 0 and m minus n2. What's m minus n2 here? N is 14, n2 is 11, n is 14, n2 is 11, 14 minus 11 is 3. Maximum of 0 and 3 is 3. Next, compute the minimum of n and n1. Next, compute the minimum of n and n1. What's n here? N is 14. What's n1 here? n1 is 9. Minimum of 14 and 9 is 9. So support of x is integers from 3 to 9. For support of x, this is capital X. Support of x is integers from 3 to 9. We have 3, 4, 5, 6, 7, 8, 9. That's support of x. Part A. What's the probability that fewer than 6 red marbles are chosen? Here x represents number of red marbles. What's the probability that fewer than 6 red marbles are chosen? That's probability that x is less than 6. That's probability that x is less than 6. Now looking at support. Support is integers from 3 to 9. If x is less than 6, x could be 3, 4, or 5. So that's f of 3 plus f of 4 plus f of 5. Then plug in. If I plug in 3, I have 9 choose 3. 11 choose 14 minus 3 is 11. Over 20 choose 14. That's f of 3. Next, for f of 4, we plug in 4 for x. Plug in 4 for x. We have 9 choose 4. 11 choose 10. 14 minus 4 is 10. Over 20 choose 14. Next, f of 5, we plug in 5 for x. 9 choose 5. 14 minus 5 is 9. 11 choose 9. Over 20 choose 14. Then use calculators. Use your calculator. Find each of them and add them up. That's the final answer. Part B. What's the probability that more than 7 red marbles are chosen? Part B. What's the probability that more than 7 red marbles are chosen? Here, x represents the number of red marbles. More than 7 means x is greater than 7. X is greater than 7. Now look at support here. If x is greater than 7, x must be either 8 or 9. If x is greater than 7, x must be either 8 or 9. So that's f of a plus f of 9. For f of a, we plug in a for x. Plug in a for x. We have 9 choose a. Plug in a for x. 11 choose 6. Over 20 choose 14. F of 9, we plug in 9 for x. We have 9 choose 9. 11 choose 14 minus 9 is 5. Then denominator is 20 choose 14. Next, use your calculator. You can get the final answer. Next, redo example 3. Assume there are 500 blue marbles, 600 green marbles, and 900 red marbles. So redo example 3. A bag contains, assume there are 500 blue marbles, 600 green marbles, and 900 red marbles. When 14 marbles are randomly chosen from the bag, find each of the following probabilities. Part A, what's the probability that fewer than 6 red marbles are chosen? Part B, what's the probability that more than 7 red marbles are chosen? Since everything is the same, everything is the same, we only change the number of marbles. We still use hypergeometric distribution. Since we only change the number of marbles, everything else stays the same. So first of all, let's set down a problem first. The X represents the number of chosen red marbles, because every problem is asking for number of red marbles, probability about number of red marbles. So the X represents number of red marbles. The X represents the number of chosen red marbles. Then X has a hypergeometric distribution. What's N? N is 14, number of chosen marbles. N is 14, number of chosen marbles. What's N1? Since X represents number of chosen red marbles, we consider red marbles as success. So here we assume there are 900 red marbles. N2 represents the number of failures. If we consider red marble as success, then blue marble and green marble, they are failures. Here we have 500 blue marble and 600 green marbles. Together we have 1100. We have 1100 failures. Next, write down the probability function. The formula for hypergeometric distribution is N1 choose X, N2 choose M minus X, over N1 plus N2 over N. Then plug in. N1 is 900, choose X. N2 is 1100, choose M minus X. Denominator N1 plus N2 is 2000. N is 14. That's the probability function. Next, support. Find the support. For hypergeometric distribution, for support, first of all, find the maximum of 0 and M minus N2. M minus N2, 14 minus 1100 is negative 1086. So the maximum between these two numbers is 0. Next, compute the minimum of N and N1. N is 14. N1 is 900. Minimum of 14 and 900 is 14. So here, support of X is integers from 0, 1, 2 to 14. That's support of X. Now answer the question. First question, what's the probability that there are fewer than 6 red marbles are chosen? Part A. We are looking for probability that X is less than 6. What's the probability that there are fewer than 6 red marbles are chosen? X is less than 6. Here, support is from 0 to 14. If X is less than 6, X could be 0, 1, 2, 3, 4, 5. That's f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. Then plugging 0, 1, 2, 3, 4, 5 into the probability function here. If I plug in 0, I get 900 choose 0, 1100 choose 14 over 2000 choose 14. If I plug in 1, I get 900 choose 1, 1100 choose 13 over 2000 choose 14. Next, f of 2 is 900 choose 2, 1100 choose 12 over 2000 choose 14. Next, plus f of 3, 900 choose 3, 1100 choose 11 over 2000 choose 14. Next, f of 4, that's 900 choose 4, 1100 choose 10, 2000 choose 14. Next, 900 choose 5, 1100 choose 9 over 2000 choose 14. Now, if we use calculator to compute this, it may be doable. The calculator may be able to handle these numbers, but those numbers are very, very big. Once, for example, 1100 choose 13, how big the number is. That's 11, for example, this number, that's 1100 factorial over 1100 minus 13 is 1100 minus 13 is 10,000, is 1087 factorial over 13 factorial. If you use calculator for each of them, your calculator may be able to handle this number, but the runtime may be very long, may be very big. The runtime for this calculation may be very big. Your calculator may be able to handle each of them individually, but runtime may be too long. Runtime may be too long. So it's doable. It's doable. You can use your calculator for the answer. It's doable. You can use your calculator for the answer. It's doable. Part B. What's the probability that more than 7 red marbles are chosen? What's the probability that more than 7 red marbles are chosen? Probability that x is greater than 7. Here, support is from 0 to 14. If s is greater than 7, that means from a to 14. X is from a to 14. a, 9, 10, 11. a, 9, 10, 11, 12, 13, and 14. Calculate each of them individually. F of a, plugging a here, 9, 10, 11, 12, 13, 14. If we plug in a, we have 900 choose 8, 1100 choose 6, 2000 choose 14. If we plug in 9, we have 900 choose 9, 1100 choose 5, 2000 choose 14. If we plug in 10, we have 900 choose 10, 1100 choose 4, 2000 choose 14. If we plug in 11, 900 choose 11, 1100 choose 3 over 2000 choose 14. If we plug in 12, we have 900 choose 12, 1100 choose 2, 2000 choose 14. If we plug in 13, we have 900 choose 13, 1100 choose 1, over 2000 choose 14. If we plug in 14, we have 900 choose 14, 1100 choose 0, over 2000 choose 14. You can use your calculator. Your calculator may be able to handle these numbers, but those numbers are are too big. Is there a better way to find the answer? Is there a better way to find the answer? Let's reconsider this problem over. Here in a set, there are 900 success, 1100 failures. In a set, assuming a set, there are 900 success, 1100 failures. If I choose one number, if I choose one element randomly, in a set, what's the chance of getting success? If I choose one element randomly, what's the probability of getting success? The chance for the first element being success is 900 over the total 2000. That's the probability for the first element being success. That's the probability for the first success. What's the probability of getting the second success? What's the probability of getting the second success? We pick one success already. What's the probability of getting the second success? Remember, probability is always number of favorable outcome divided by number of all possible outcome. We pick one success already. There are 899 success left. Totally, if I pick one success, there are 1,999 elements left. So the chance for the second success is 899 over 1,999. That's very close to P1. Right? You can see that this number is very close to P1. If we use calculator, these two numbers, they are very close. What's P3? What's the chance of getting the third success? What's the chance of getting the third success? Also, we pick two success already. What's the chance of getting the third success? Since we pick the third success, number of favorable outcome is 898. There are 898 success left. Divided by the number of all possible outcomes, there are totally 1,998 elements. That's the chance of getting the third success, which is also very close to P1 if you use your calculator. This number is also very close to P1. So if we keep going, we are choosing a total of 14 elements. The chance for the 14th success is 800. In this problem, we are choosing a total of 14 elements. And the chance for the 14th success is 886 over 1,986. If we use calculator, we can see that this number is also very close to P1. So we see that for the first 14, we are choosing a total of 14 marbles, 14 elements from the set. The probability of getting success for the first 14 elements, they are all very close to each other. So if they are all the same, if the probability of getting success is the same for every trial, if the probability of getting success for every trial is the same, that looks like a binomial distribution. If the probability of getting success for every trial is the same, it looks like a binomial distribution. So here we can try to use binomial distribution to approximate hypergeometric distribution. Here we can try to use the binomial distribution to approximate this hypergeometric distribution. So when the sample size is very big, we can try to use binomial distribution to approximate the hypergeometric distributions. So note, keep this idea in mind. When n1 plus n2 is much larger than n, when the total number of elements is much larger than the number of chosen elements, we can use binomial distribution to approximate hypergeometric distribution. When the total number of elements is much larger than the number of chosen elements, we can use the binomial distribution to approximate hypergeometric distribution. Because when the total number of elements is much more than the number of chosen elements, probability for each trial is almost the same. Probability of getting success for each trial is almost the same. When the sample size, when the number of total elements is much more than the number of chosen elements, the probability of getting success for each trial is almost the same. So we can use binomial approximation to approximate hypergeometric distribution. And the runtime for binomial distribution is much shorter than hypergeometric distribution. Next, let's redo example 4. Using binomial approximation. Using binomial distribution, to approximate hypergeometric distribution. So we are using binomial distribution to approximate hypergeometric distribution. The theta is the same. The x represent number of chosen red marbles. The x represent the number of chosen red marbles. Here we are using binomial distribution. We're using binomial approximation. When we are using binomial approximation, for binomial distribution there are two parameters, n and p. What's n? What's p? N is number of trials. In binomial distribution, n is number of trials. Since we are choosing 14 elements, that means we have 14 different trials. So n is 14. N stays the same. How about p? P represents the chance of getting success for each trial. P represents the chance of getting success for each trial. Probability is always number of favorable outcome divided by number of all possible outcome. Success is number of favorable outcome, which is 900. All possible outcome. Every element could be chosen. Every element could be chosen. So total number of all possible outcomes is 900 plus 1100, which is 2000, which is 9 over 20. That's P. So this X is binomial distribution with n equal to 14, P equal to 9 over 20. So keep one idea in mind. When we use binomial distribution to approximate hypergeometric distribution, when we use binomial distribution to approximate hypergeometric distribution, n stays the same. And P is always n1 over n1 plus n2. N stays the same. And P is always n1 over n1 plus n2. Here, originally, n is 14. When we're using hypergeometry, n is 14. When we're using binomial approximation, n still 14. And P is n1 over n1 plus n2. 900 over n1 plus n2, which is 2000. So, when we're using binomial distribution to approximate hypergeometric distribution, n stays the same. P is always n1 over n1 plus n2. Next, let's run the probability function. For binomial distribution, the probability function is n choose x, p to the power of x times 1 minus p to the power of n minus x. That's the formula for binomial distribution. And the support of x. For binomial distribution, support is much easier. 0, 1, 2 up to n. N is 14 here. For probability function, we need to plug in numbers. N is 14. P is 9 over 20. 1 minus p is 11 over 20 to the power of n minus x. So that's the setup. Now let's answer the question. Part A. What's the probability that x is less than 6? Part A. What's the probability that x is less than 6? Probability that x is less than 6. That's same thing, f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. F of 0, plug in 0 for x. That's 14 choose 0, 9 over 20 to the power of 0, 11 over 20 of m minus x. N is 14. It should be 14 minus x. 14 minus 0 is 14. That's f of 0. F of 1 is 14 choose 1, 9 over 20 choose 1, 11 over 20 choose 13. Next is 14 choose 2. F of 2 is 14 choose 2, 9 over 20 to the power of 2, 11 over 20 to the power of 12. Next, f of 3 is 14 choose 3, 9 over 20 to the power of 3, 11 over 20 to the power of 11. Next is 14 choose 4, f of 4 is 14 choose 4 times 9 over 20 to the power of 4 times 11 over 20 to the power of 10. f of 5 is 14 choose 5, 9 over 20 to the power of 5, 11 over 20 to the 9. Then use your calculator. In general, if you compare this computation here, calculate this, the number is much less than this expression here. If you compare these two expressions here, it's still long, but the numbers are much smaller than this expression. The number here are much smaller than the number here. Those numbers are much smaller than these numbers. It's still long, but it's much easier. The long time will be much shorter if you use this expression. Their answer will be very close to each other. Their answer will be very close. This is an approximate answer. It's very close to the actual answer. But the long time is much shorter. If you calculate this, the long time is much shorter than this. That's part A. Now for part B. Part B, we're looking for probability that x is greater than 7. Part B, we're looking for probability that x is greater than 7. Here, suppose of x is from 0 to 14. If x is greater than 7, we have f of a plus f of 9 plus f of 10 plus f of 11 plus f of 12 plus f of 13 plus f of 14. Then plug this number into the formula here. Plug this number into this formula here. We have 14 choose A, 9 over 20 to the power 8, 11 over 20 to the power of 6, plus 14 choose 9, f of 9, 14 choose 9, 9 over 20 to the power of 9, 11 over 20 to the power of 5, plus 14 choose 10, 9 over 20 to the power of 10, 11 over 20 to the power of 4, plus 14 choose 11, 9 over 20 to the power of 11, 11 over 20 to the power of 3, plus 14 choose 12, 9 over 20 to the power of 12, 11 over 20 to the power of 2, plus 14 choose 13, 9 over 20 to the power of 13, times 11 over 20 to the power of 1, plus 14 choose 14, 9 over 20 to the power of 14, (11 over 20 to the power of 0). If we compare these two expressions, we can see that in this expression, the numbers are much smaller than the number in this expression. The same number of terms, but the number here are much smaller than the number here. It's still long, but the long time will be much shorter than this. It's much better than this expression. It's much better than calculate this directly. It's still long, but calculate this, the long time is much shorter. It's much better than doing this over. So, using binomial approximation, when we use binomial distribution to approximate hypergeometric distribution, their answers are very close to each other. But the long time, if you compare the long time, binomial distribution will be much shorter than hypergeometric